There is a sheet of paper on a table in front of you. If the length of that sheet represents the distance between where you are now and some chosen destination, then the time required to reach it follows directly from the most elementary equation in physics. Distance divided by speed equals time. This is true whether the journey is across a room, across a continent, or across the void between galaxies. The Andromeda galaxy sits roughly 2.537 million light-years from our own. At any speed a human civilization has yet to achieve, the travel time is not merely long. It is, in any practical sense, incomprehensible. And yet the paper is still lying on the table, and it has something to tell us. Pick it up, fold it so that the two short ends meet across the length of the sheet. The distance measured along the surface of the paper, that is, in the plane you were originally thinking in, has not changed at all. The inches are still there, still real, still traversable in the way you always imagined traversal to work. But in the direction perpendicular to that plane, in the dimension made available by the act of folding, the two ends of the paper are now almost touching. What was a journey of the full length of the sheet has been collapsed, in that new direction, to the width of two sheets of paper pressed together. The distance did not shrink. A new geometry became accessible. This is not merely a metaphor. It is the underlying intuition behind some of the most serious and strange corners of theoretical physics. The idea that the structure of space itself, across scales we have no instrument to directly probe, may be folded in ways that render vast distances trivial in directions we do not yet know how to walk. The universe, as best we can tell, is not a flat surface extending uniformly in 3 dimensions toward an infinite horizon. It has curvature, it has topology, and topology permits configurations that are deeply counterintuitive to beings whose entire experiential repertoire has been constructed at one scale in one region, moving in the dimensions that evolutionary pressure made legible to them. Consider a second image. You are standing on the surface of a sphere. Not metaphorically, this is already true of you, and you have, until this moment, known only how to walk forward. You face some arbitrary direction. Behind you, at a distance that represents a large arc of the sphere's circumference if approached by continuing forward, is your destination. To reach it by the only method you know, you must walk the long way round. You must traverse most of the perimeter before arriving, and then someone tells you that it is possible to walk backwards. The destination behind you is, in that direction, close. The distance was never the problem. The constraint was the vocabulary of movement you had inherited. The analogy matters because the limitation was not ignorance of the destination's location. It was ignorance of a degree of freedom. Once the new direction becomes thinkable, what was formerly an odyssey becomes a step. The Andromeda galaxy is 2.537 million light-years away, in the dimensions we habitually occupy and measure. Whether it is also trivially close in some higher dimensional sense, whether the universe is folded such that the gap is, in directions we have not yet learned to walk, a step rather than an epoch, depends on the actual topology of space-time, which remains at the largest scales genuinely unresolved. But the question is no longer metaphysical speculation. It is a geometric one, and geometry has answers, even when we do not yet have the instruments to find them. But intuition, however elegant, is not physics. The question is whether the fold is real, not as metaphor, not as thought experiment, but as a structural feature of the universe that obeys equations and carries consequences. The answer, unsettlingly, is that serious mathematics has been pointing in this direction for over a century, and the pointing has only become more insistent. In 1921, the mathematician Theodore Kaluza sent Einstein a paper proposing that space-time had not 4 dimensions but 5. The 5th was spatial, real, and compactified, curled into a circle so small that no instrument of the time, and arguably no instrument since, could resolve it directly. What Kaluza showed was that general relativity extended into this 5th dimension naturally produced, without any additional assumptions, the field equations of electromagnetism. 2 forces, previously unrelated, unified by the introduction of a direction too small to walk in. Klein later estimated the scale of this compactification at roughly the Planck length, 10 to the power of -35 meters. The dimension is not absent. It is folded beyond our resolution. This is the paper fold stated in the language of differential geometry, a direction that exists, that has physical consequences, but that is invisible to beings whose instruments and intuitions were built at a scale some 28 orders of magnitude too large to perceive it. String theory does not add one such dimension. It requires 10, or in its M-theory formulation, 11. 6 or 7 of these are compactified, their geometries, described by what are known as Kaluza-Klein manifolds, determining the physical constants of the universe we observe at our scale. The topology of those folds, the specific way the extra dimensions are curled and knotted against each other, sets the values of the parameters we measure in laboratories and call fundamental. We are, on this picture, not inhabitants of a three-dimensional universe that happens to have a time axis. We are inhabitants of one particular fold of an 11-dimensional structure, and the physics we have spent centuries cataloging is the shadow that fold casts at our scale. The paper is not a metaphor. The paper is the cosmos, and we are creatures who have, so far, only learned to read its surface. General relativity permits something more direct. Einstein and Rosen showed in 1935 that the field equations, without modification or extension, allow for solutions describing a throat, a tunnel through the geometry of spacetime connecting two regions that are, measured along the surface, arbitrarily far apart. An Einstein-Rosen bridge. That same vast interval between here and Andromeda is a surface measurement, the distance along the unfolded sheet. A wormhole, if one exists connecting our region of spacetime to that galaxy, would be the fold made traversable, not a violation of the speed of light, but a renegotiation of what counts as the distance between 2 points. The objection is immediate and fair. Such structures, in their classical form, are not stable. They collapse before anything could pass through them. Threading them with exotic matter, matter with negative energy density, could in principle hold them open. Whether exotic matter exists in the required form remains unresolved. The geometry is permitted. The engineering is not yet in hand. Miguel Alcubierre's 1994 paper proposed something that reads, on first encounter, like science fiction presented in the notation of general relativity. A metric, a precise mathematical description of a region of spacetime, in which a bubble of flat space is carried through the universe by contracting the spacetime ahead of it and expanding the spacetime behind it. The vessel inside the bubble does not move through space. The space moves. The local speed of light is never violated, because locally nothing is moving at all. What changes is the geometry of the space between the origin and the destination. The sheet, folded while the traveler sits still inside a region where physics proceeds normally. The cost is the same as the wormhole: exotic matter, negative energy density, magnitudes that current physics cannot produce and may never be able to. But the Alcubierre metric is not a fantasy. It is a solution to Einstein's field equations. The universe's own rules, applied without approximation, produce it. The question is not whether the geometry is valid. The question is whether the matter conditions required to realize it are physically achievable, and that question is open. The paper is still on the table. The fold is demonstrable in the mathematics, permitted by the field equations, demanded by string theory's account of why the universe has the constants it does. What remains is not a question of whether higher dimensional structure is real, but whether we will ever find the direction in which to walk. The distance to Andromeda has not changed. The geometry, it turns out, may have always been more accommodating than the distance implied.